So far, we have learned a lot of things about motion, but we have not yet defined what is exactly motion. So let's now look at the accepted definition of motion. So a body is said to be in motion if it changes its position, if it changes its position with respect to its surroundings. So now, so far we have already focused on the aspect of changing the position, right? So we already know how to measure the change in position. We saw how position of an object can be defined by its coordinates, or we can also define it using a position vector. So we know how to measure position, how to define it. So whenever position changes, it will said to be in motion. But let's now focus on this with respect to surrounding part. So we are going to be focusing on this with respect to surrounding part. What does this mean? So let's understand this through a simple example, a very typical example. Let's say two people are moving on a cart. Let's give them names as A and B. And let's say there is a friend of theirs is on ground. Let's call him C. So A and B are moving in this cart, which moves with a constant velocity V in this direction. Now, notice that when we talk about constant velocity, it means that the direction as well as the magnitude cannot change, right? Because velocity means speed as well as direction. So constant velocity would imply that this collection of things like A, B and this cart, if they're moving with a constant velocity, they're not changing their speed as well as they're not changing their direction. So we did not discuss this so far, so let me just make a mention of this, that constant or uniform velocity so a constant or uniform velocity implies that speed as well as direction are constant. So neither the speed nor the direction will change, right? So such a motion is also called uniform motion, right? So A and B, who are on a cart, are basically going through a uniform motion. Now, let's think of a discussion between A and C. So when A talks to C about what B is doing, he tells C that B is not moving. You can think about this. If you and your friend are sitting in a bus or moving in a train, you don't see your friend as moving, right? You feel as if he's sitting next to you and he's stationary, although the bus is moving. Same is the case here. When A looks at B, he says that B is at rest. But C, who's standing on the ground, says that he can clearly see that B is moving with a speed V. So who's correct? Well, it so happens that both of them are correct. This is why we made a mention of surroundings. So, motion is not absolute. That is, we cannot isolate an object or take any object and say that this is in motion. We also have to define with whose respect are we defining whether it is in motion or not. What this means is, when we are questioning whether or not B is moving, we must specify with respect to whom this question is being asked. For example, in this case, if you ask A, he would say B is not moving, whereas C disagrees and he sees that B is moving. So, motion is always relative. So, motion is relative, which means that depending on who is observing a particular object, that object could be in motion or it could be at rest. Right. So this gives rise to the idea of observers. So basically observers are the person or a frame with respect to whom we are analyzing an object. For example, in this case, while we are analyzing B, we have two observers A and C. Right. Now, another term which is used is called frame of reference. So, frame of reference is nothing but you could say it is the observation of an observer which is being called a frame of reference. For example, if you choose to view this motion through C, then your frame of reference is the frame in which C is standing, which is the ground. Whereas, if you choose to see it through the observation of A, then you're choosing the cart frame because A is riding the cart. So, frame of reference is just the name given to the way we are observing or the place where the observer is standing, right? So in this frame of reference, one frame that you typically would hear about is ground frame. So ground frame is a frame, you could say, as the name suggests, would be the frame of reference of an observer who's standing stationary on ground. Like in this case, we could say that C is a ground observer or that the frame of reference of C is the ground frame. So ground frame is basically the frame that we assume is stationary, right? So we understood that a particle is said to be in motion if it changes its position, but whenever we talk about motion, we are always talking about somebody's observation. And these observations will change as you change the observer, or as we said, if you change the frame of reference, right? So let's take a simple example and see how sometimes understanding that motion is relative can simplify a certain analysis. So let's say there are two particles A and B which are at a distance of 250 meters. So now A starts to move towards B at the speed of 10 meter per second and B is moving towards A with the speed of 15 meters per second. Right. We have to find the time after which they meet and the position at which they will meet, right? So, to analyze this motion, let's first of all again think about the observers, because we just understood that motion, the description of motion is incomplete till you specify the observer, right? So looking at the problem, you already see we are given two velocities 10 meter per second and 15 meter per second without specifying whose observation these are. So basically in such cases, we say that these observations are with respect to ground frame. That is the frame that we are assuming to be stationary, right? So in this frame, let's first of all try to solve this problem where we have to find the time and the position where A and B meet, right? So they both start simultaneously and clearly they'll meet simultaneously, right? It cannot happen that A meets B before B meets A, right? So the time for which A moves is same as the time for which B moves. So let's say that this time is T. So T is the assumed time after which A meets B, right? So during this time, let's say the distance covered by A is SA. Now, we know that distance covered is equal to speed into time. So the distance covered by A can be written as 10 into T, right? Similarly, distance covered by B can be written as the speed of B, which is 15, into time. So this is simple. We have simply written distance is equal to speed into time. So distance for A becomes 10t, distance for B becomes 15t. Also, if you observe, the distance covered by A plus the distance covered by B, I've indicated them by these arrows. You can clearly see that this is SA and this is SB. So the sum of distances covered by A and B has to be equal to 250, right? That means SA plus SB is equal to 25t. Now, from our conclusions, the sum should add up to 250. From the equations, we can see that SA plus SB is nothing but 25t. So solving this, we see that t is equal to 10 seconds. So they will meet after 10 seconds. And substituting these values, you can clearly see that distance covered by A would be 100 and distance covered by B would be 150 meters. So they will meet at a point which is 100 meters from A and 150 meters from B. Right. So this is one way to solve this problem. In this case, I want you to notice what we did is we declared one variable which was time, and then on the second variable, which is the distance, we built a constraint. That is, their sum is 250. We could do the opposite also. That is, we could assume the distance and then build a constraint on time. Let me show you how. We could say that, let's say the distance covered by A is x. Now, if A has covered the distance x, then the remaining distance would be 250 minus x, since their sum must be 250, right? So we are using the same logic, only our reference variable has changed. That is, I'm saying this time the variable I'm assuming is the distance covered by A. So I've said that the distance covered by A is x, and hence the distance covered by B should be 250 minus x. Now, to build the equation, I'll use the second constraint, which is the constraint on time, which is that they both must have taken the same time, right? So, we know the distances, we have to find time. How do we do that? Distance by speed gives you time. So, the time taken by A would be x divided by the speed of A, which is 10 meter per second. So, x by 10 is the time taken by A. Similarly, when we talk about time taken by B, we can write it as 250 minus x divided by 15. And I've equated these two because the time taken by A has to be equal to time taken by B. Now, if you solve this equation, you'll once again get that x is equal to 100. So, both these approaches are same. The only difference is that in this case, we assume t to be a variable. The working variable, you could say, that is, you've made an assumption that time is t, and then you are using this variable to build equations. And in this case, you declared x, and then you used this variable to build your equations. Right. So, in this current form, we have solved this problem from the ground frame. Now let's try to change our observer. Let's try to make A our observer and then look at this entire event as A would see. So this is the situation that A is here and B is here. Right. Now, when A looks at B, would he still feel that B is moving at 15 meters per second? To understand the situation, let's think of a situation that you might have seen. Let's say you're sitting in a car. You see a car approaching you. You notice its speed. Now, you yourself start moving towards the car. What happens to the speed of the approaching car? Would you see a difference? You would, right? You would feel as if that approaching vehicle is now approaching at a higher speed. So that means as you start to move, your observation about another object changes, right? Same is the case with A. A would not feel that B is coming towards him with 15, but rather he would feel that he is coming towards him at a much faster speed. Right. Now, we will not go into the details of this right now. We'll come back to it later. But just for the sake of this problem, think about the speed with which A would feel B is coming towards him. I'm sure you can guess this. He would feel that B is coming towards him at 25 meters per second. Right? So what he'll actually do is he will assume that he is stationary. Every observer feels the same. Even when you're moving in a bus, you feel as if you're stationary and everything else is moving backwards. So this is the way an observer works. He always assumes that he's stationary and everything else is moving. So according to A, he would be stationary and B is coming towards him at a speed of 25 meters per second. And he knows that distance between them is 250 meters. So for A, this problem is very simple. He sees that the distance is 250 meters, the speed of B is 25 meters per second, so he can easily tell you that the time after B reaches him is 10 seconds. So we saw how if you choose a suitable observer, the problem can be really simplified. And this is something we will learn as we move along. Right. So in this session, we understood the definition of motion. We understood that motion can only be described after specifying the observer, that is, who is observing the entire event. Right. So in the next session, we will now look at the equations of motion. Thank you.